Today's submitted material offers a comprehensive overview of the Stuxnet worm, detailing its origins, its zero-day exploits, and its physical impact on Iran's Natanz nuclear facility. Let's dive straight into the feedback.
Yeah, let's do it. So the analysis of the infection vector is engaging, but it stops short of detailing the precise software subversion that actually blinded the system operators.
Right.
And, the core weakness here is that because the target audience is security professionals, the material spends like a disproportionate amount of time focusing on the initial air gap jump.
Yeah, the USB drives.
Exactly. The USB drives and, the 4 Windows zero-day vulnerabilities. But then it ends up just glossing over the specific man-in-the-middle attack executed on the industrial control systems themselves.
It tells the reader that the centrifuges were destroyed, but it doesn't adequately explain the localized manipulation of the supervisory control and data acquisition, the SCADA systems.
Right, exactly. It feels like half the story.
It really does. I mean, knowing about the Windows Zero days is helpful context, obviously. But for an ICS specialist, Windows is kind of just the delivery truck.
Yeah, that's a good way to put it.
The true payload targeted the physical machinery. So the suggestion here to improve this is to deepen the technical explanation of the SCADA subversion, specifically detailing how the malware intercepted communications between the Windows-based control software and the Siemens Programmable Logic Controllers, or PLCs.
Yeah, and to do that effectively, they really need some concrete examples. Like, the author needs to unpack the actual mechanics of the .dll hijacking.
The DLL hijacking?
Yeah.
The piece mentions the S7OTBDX.dll file.
Yeah.
But it doesn't really explain why targeting that specific dynamic link library was so devastatingly stealthy.
So a DLL is basically a shared library of instructions, right?
Right, exactly. It's what programs call upon to execute functions.
And Stuxnet essentially replaced the legitimate Siemens DLL with its own malicious version.
Oh, wow. So when the Siemens Step 7 software tried to read the PLC logic or send a command, it wasn't actually talking to the hardware anymore.
No, not at all.
It was talking to Stuxnet.
Exactly. It severed that honest communication channel entirely. By injecting the malicious code right at the library level, Stuxnet drove this wedge between the software giving the commands and the hardware executing them.
So it became the sole arbiter of truth for both sides.
Yeah, it was running the show. And this naturally leads into the physical damage. But again, the text just states the what and skips the how.
Right, I noticed that too.
Like, the source material briefly notes that the centrifuges usually spun between 807 Hz and 1210 Hz, and that Stuxnet altered this. But, why does changing the speed actually destroy them?
Right, it's not just about making them go fast.
No, the author needs to give the example of the physics of resonance frequencies. You don't just speed up a motor to break it, you have to hit its structural weak points.
And that is a critical missing link for a technical audience.
Absolutely.
Like, the code spent weeks just monitoring the baseline, right? Mapping out the normal operating parameters.
Yeah, it was super patient. Once it understood the physical limits, another concrete example the author should include is how it spiked the frequency to 1410 Hz for 15 minutes.
Just to stress it.
Right. And then days later, it drastically dropped the speed down to just 2 Hz for 50 minutes.
Oh, wow. Just 2 Hz.
Yeah, and spinning at 2 Hz isn't just slow. It causes the aluminum centrifugal tubes to literally lose their gyroscopic stability.
They start to wobble.
Severe wobble. And when you have an array of thousands of delicate tubes spinning with millimeter clearance, that wobble forces the rotors to make physical contact with the outer casings.
That's terrifying.
Yeah, they literally rip themselves apart from the friction and structural stress. The author needs to explicitly describe how the excessive stress from those wildly fluctuating speeds manipulated the physical resonance.
Okay, but here's where I get caught up as a reader. I understand the motor was wobbling and tearing itself apart, but why didn't the technicians just hit the emergency stop button?
Right, the monitoring.
Yeah, I brought up this idea in my notes that to synthesize this technical data, the author could compare the DLL subversion and fake feedback loop to a Hollywood heist. Like where a compromised security camera feeds a pre-recorded loop of an empty hallway to the guards while the vault is being emptied.
Oh, I like that.
Yeah, Stuxnet basically recorded normal operations and just played them back, right?
The heist analogy is really fun, yeah. But we have to remember it's a bit simplified for this specific audience.
Okay, fair.
Because, a bank guard just looks at a single video feed. A SCADA operator in a nuclear facility is looking at pressure gauges, flow rates, network traffic, secondary vibration sensors.
It's a massive dashboard.
Exactly. So how did Stuxnet fool all of those interconnected systems for nearly a month without tripping a single analog alarm?
That's a fair challenge. So it wasn't just a simple video loop then?
No, it was way more complex. The rootkit functionality had to intercept every single query coming from the monitoring software and calculate exactly what a normal response would look like under those specific fake conditions.
Wow.
It literally fed the operators 30 days of perfectly normal, dynamically generated simulation data. Pressure, speed, temperature, all while the rotors were crashing in reality. The author really needs to explain that this wasn't a blind loop.
It was an active simulation of normalcy.
Yes. And, if Stuxnet is feeding operators a highly sophisticated, dynamically generated fake reality, literally lying to their faces while destroying the plant, then telling those same operators to simply check their antivirus to prevent it is completely useless.
Which is a perfect segue.
Right, it brings us directly to the next point. The recommended defensive measures lean too heavily on standard IT practices rather than addressing the unique architectural demands of industrial control systems.
Yes, that's a huge weakness in this piece. The text provides really generic advice. Things like using strong passwords, updating antivirus software, and applying patches.
Which is fine for an office, but...
Right, exactly. While these are foundational IT practices, they completely fail to address the specific vulnerabilities of PLCs and variable frequency drives. A security professional reading this needs actionable intelligence on how to defend an industrial environment, not just an office network.
Yeah, the author is basically giving office network advice for a factory floor problem. Because in an IT environment, the priority is data confidentiality, right? If a computer crashes or a file is locked, you lose some data. Maybe you just restore from a backup.
Right, it's an annoyance.
But in an operational technology or OT environment, the priority is safety and continuous operation. If an antivirus scan unexpectedly quarantines an industrial control process, you could cause a catastrophic physical event.
The software itself becomes the hazard.
Exactly. Antivirus on a critical PLC controller is often way more dangerous than the malware itself.
So the suggestion here is to pivot the recommendations to focus exclusively on ICS-specific security frameworks and physical defense in-depth strategies that counter the specific technical threats we just talked about.
Definitely.
So for concrete examples, rather than just saying update your firewall, they should recommend specific memory auditing practices, right? Like regularly auditing PLC memory blocks.
Yeah, they need to look at specific PLC memory blocks, like DB890.
DB890?
Yeah, think of DB890 like the hidden trunk of a car. It's this deep storage area in the controller's memory where Stuxnet specifically hid its monitoring and execution code.
Ooh, sneaky.
Yeah. If defenders are just checking the dashboard, the operating system, they'll never find it. If you aren't popping the trunk to audit those deep memory blocks, you aren't doing a real ICS audit.
I'm curious, though, about the structural defenses. Like, the author mentions the air gap at Natanz, but they treat it almost like an impenetrable wall that just happened to fail this one time.
Right.
Is there a risk that focusing heavily on software patching might give a false sense of security in an ICS environment, considering Stuxnet bypassed software entirely to manipulate physical motor frequencies?
Oh, absolutely. And, the air gap itself is largely a myth in modern industrial environments anyway.
Really?
Yeah, people carry USB drives across physical air gaps every single day. You've got maintenance laptops, vendor updates, USB diagnostics data is always crossing that threshold.
So what's the better approach for the author to suggest?
To give a concrete example for improvement, the author needs to advocate for strict network segmentation. Specifically, they should detail the implementation of demilitarized zones, or DMZs, between general business networks and industrial networks.
Okay, so creating a buffer.
Right. A DMZ creates a hardened buffer zone with highly restricted, inspected traffic. You don't just rely on physical isolation. You rely on heavily monitored architectural choke points.
But even with a DMZ, if the attacker compromises the very software that tells you if you are under attack, like we saw with the fake dashboard, you're still flying blind.
You are.
This is where the defense in depth strategy really has to include physical components. The author briefly touches on a power grid attack in Ukraine, but they miss the fundamental takeaway of why that attack is so relevant to ICS defense.
Yeah, the Ukrainian grid attack is the perfect case study here. The author should absolutely expand on it to make a concrete point about hardware-based manual overrides.
Manual overrides.
Yeah. In that incident, hackers successfully infiltrated the network and brought down a massive portion of the electrical grid, like in the dead of winter. It was a highly coordinated digital strike.
But they got it back online really fast, right?
Exactly. It was brought back online surprisingly quickly compared to what would happen in a fully modernized Western grid.
Because their systems were older and they actually had old-school manual overrides that most modern systems lack.
Right. Most modern, fully automated systems rely entirely on digital relays. But if the digital brain is infected, you have to sever the connection to the physical body.
You need a physical switch.
Exactly. In Ukraine, operators could literally jump in a truck, drive out to a substation, and physically pull a heavy mechanical lever to reconnect power and just completely bypass the compromised digital controllers.
That's amazing.
So advocating for the retention or even installation of hardware-based manual overrides is a deeply practical, ICS-specific recommendation. It elevates this material far beyond just change your passwords.
It brings the defense back to the reality of the physical world. It's a tangible solution. However, this kind of leads us to the final major area of the text.
Yeah.
The narrative treats Stuxnet as a standalone historical anomaly, rather than the foundational blueprint for modern industrial cyber weapons.
Yes, and the core weakness here is that by concluding the technical analysis at the Natanz facility, the material just totally fails to connect Stuxnet's underlying mechanisms to the subsequent real-world evolution of ICS-targeted malware.
Right. It misses the so what for a modern security professional.
Exactly. It leaves the impression that this was just a one-off geopolitical event rather than a permanent shift in the threat landscape.
I want to talk about that so what, though. The source text briefly mentions this idea of a Pandora's box moment because the code was decompiled. If the code is now out in the wild, does that mean the barrier to entry for creating a Stuxnet-level event has been permanently lowered for non-state actors?
Yes, 100%. It's essentially an open-source blueprint now.
Wow.
When the security community caught the worm, they decompiled it, meaning they reverse engineered the compiled executables back into readable source code. And, if the white hat researchers can read it, so can the black hat operators.
So they just copy it?
Well, Stuxnet wasn't just a single weapon. It was an incredibly sophisticated modular framework. It taught the world how to reliably exploit Windows to jump an air gap, how to hide inside a Siemens PLC, and how to spoof those SCADA monitoring screens.
So the suggestion for the author is to broaden the scope of the conclusion to demonstrate how Stuxnet's modular, physical damage approach basically birthed a new lineage of threats.
Exactly.
Show how the open box of Stuxnet's decompiled code serves as a template for ongoing attacks. What are some concrete examples of malware they could use to show that direct technical lineage?
They should definitely start by drawing technical parallels to Duke.
Duke? Okay.
Yeah, Duke was discovered not long after Stuxnet, and it was nearly identical in its architecture. It used the exact same underlying framework. But the author should explain how Duke repurposed that framework.
What did it do differently?
Instead of destroying equipment, it was modified specifically for logging keystrokes and gathering deep reconnaissance from industrial facilities.
Oh, so it was like the intelligence-gathering cousin to Stuxnet?
Precisely. It proved that the codebase could be easily adapted for entirely different goals.
That's a great example. Another highly relevant example the author must mention is Industriware, right?
Oh yeah, Industriware is vital.
They should tie its power facility targeting directly to the legacy of Stuxnet's critical infrastructure focus. Because Industriware proved that the capability had made the leap from highly classified nuclear enrichment programs to civilian electrical grids.
Right. It demonstrated that non-state actors or, less sophisticated nation-states now had the capability to plunge a city into darkness using automated ICS protocols.
Which is terrifying.
It is. But To really drive home the severity of this evolution, the author absolutely must highlight Triton as a concrete example.
Yes, Triton represents a terrifying escalation. The author needs to explicitly note how Triton specifically targeted the safety instrumented systems of a petrochemical plant.
In the Middle East, yeah.
But again, we need the HOW, not just the what. How did Triton actually manipulate those safety systems?
So Triton is a masterpiece of dangerous engineering. It targeted Triconex's safety controllers. And these are the absolute last line of defense in a chemical plant, designed to shut everything down if pressure gets too high, basically preventing an explosion.
So with the emergency brake.
Exactly. And Triton worked by exploiting a zero-day vulnerability to inject a remote access Trojan directly into the firmware memory of those safety controllers.
Oh my God.
Yeah. It didn't just blind the operators, it actively disabled the emergency brakes of the entire plant.
So while Stuxnet was designed to destroy equipment, which is costly and disruptive, Triton was designed to remove the safeguards that prevent catastrophic explosions.
Right.
The author needs to emphasize that this elevates the threat from mere equipment destruction to potential physical injury or death of workers.
And that is the ultimate so what for the reader. It completely reframes the conclusion.
It really does.
It moves the reader from thinking, wow, that was a crazy thing that happened to some centrifuges a long time ago, to this technology is currently being iterated upon to target the safety systems, keeping my local power plants and chemical refineries from exploding right now.
It places the reader right in the crosshairs of the modern threat landscape.
Exactly. It transforms the text from an engaging, historical retrospective into a vital, forward-looking piece of security analysis.
So to summarize this critique, the source material provides an excellent historical narrative, but can be significantly strengthened for security professionals.
Yeah, definitely.
First, by deepening the technical explanation of the PLC subversion. Second, by replacing generic IT advice with specialized ICS defense in-depth strategies. And finally, by contextualizing Stuxnet as the direct ancestor of modern threats like Industroyer and Triton. The listener is invited to implement these actionable suggestions and submit their revised work back in for another critique.
I really look forward to reading the next iteration. Once those technical mechanisms are fleshed out, it's going to be an incredibly impactful read.
I agree. Until next time, keep questioning what you see.